Next presentation is Maaike Blauw on the subject of BioGrout.
Yes.
Please, the floor is yours. The floor is yours.
Oh, thank you very much. Another FloodPro presentation. I will present our results for Work Package 4, a part of Work Package 4. And in the last 3 years, we did some research to see whether BioGrout and strengthening process could be a new measure to prevent internal erosion. And I did this together with a lot of other colleagues. They did the flood defense part, and I did with the marine the BioGrout part. Well, internal erosion, as you would all likely know, is an important potential type of failure for flood defense systems, and they often don't know where the internal erosion would occur. They have some ideas, but they don't know when it would occur. And when they have a suspicion when it could occur, there are traditional mitigation or prevention measures at the moment to prevent internal erosion, like increasing the leakage path, placing berms, or like blocking erosion paths with sheet piles, grout injections, and filters. However, these traditional measures have their disadvantages, like high costs, need of space for the berms, and hindrance to the environment, like settlements and excavations, stuff like that. So as internal erosion is still a very important type of failure for the flood defense system, we were thinking, could BioGrout be a possible additional measure to prevent internal erosion? First, I would go a little bit deeper into BioGrout. Maybe not all of you would know what BioGrout is. Well, BioGrout is actually an in situ strengthening process using bacteria. By injecting bacteria into the soil and calcium and urea, the bacteria will convert the urea to ammonium and to carbonate, and the carbonate will precipitate because there's a calcium ion also injected into it. Because the bacteria get stuck between the sand grains, at the boundaries of the sand grains, you get mainly calcite precipitation at the boundaries of sand grains. So you don't have a loss of porosity, but you'll get a increased strengthening of your soil. The main advantages of BioGrout is that you can apply it in situ. It's a very watery solution we inject. So that's why we also can reach large injection distances, over 5 meters. And the strength and stiffness are adjustable between 0.2 megapascal, that's only just slightly strengthened soil, you can smash it with your hands, up to 50 megapascal, and that's concrete strength. And as I said before, the porosity will be maintained up to 10 megapascal, because the more urea and calcium chloride you'll inject, the more calcite you'll get, the more strength you'll get, but also the more your pores will get clogged. Light application materials used because it's only watery solutions what we inject, and at the end only calcite is left into the soil. There, of course, there's a couple of points of attention with this process. It can only be applicable in soils that are permeable, because we have to flow the bacteria and the urea and calcium chloride. We produce ammonium chloride, and this has to be removed and has to be treated. So that's a very important point. Therefore, it's also a high-grade technology, and at the moment we only have experience in saturated soils. Very quick, the development of BioGrout. We developed it at Deltade since 2005. We started with small columns. Then 3 years ago, our first cubic meter, a spherical BioGrouted sand sample. In 2009, our first container experiment, 100 cubic meters, where we have the injection distance of 5 meters. And at the end, in 2010, our first field application to strengthen gravel for horizontal drilling. So with BioGrout, we strengthen the soil. Therefore, we suspect that we prevent erosion, but at the same time, because the water flow isn't stopped, we won't move the problem, because the water flow still goes on, but we just stop the process of internal erosion. So we want to investigate, is BioGrout effective for backward erosion, and can we apply it in the field? What does it mean if we want to apply it in the field? And we've got 3 research topics. The first one was the shape, location, and required strength of BioGrout. The effectiveness of BioGrout near clay layers, because often the backward erosion occurs between a transition zone of clay and sand in Holland. So we want to see if the BioGrout attaches well to the clay layers. And what does it mean for BioGrout in the field? Well, the first research point is the shape. This has been with groundwater flow models and expert knowledge, deltares. The shape of BioGrout has been determined. The thickness should be about 30 centimeters. Actually, a thin wall of 1 millimeter would be sufficient if all the grains would be glued together. But of course, because there is heterogeneity in the soil, different stabilities, we will aim at least about a thickness of 30 centimeters, so we know for sure there will be one wall of strengthened soil. And the depth of the BioGrout will be about for 1 meter, it's calculated, if it's a 3 meter thick sand layer and 50 meter seepage length. And here you could see a schematic overview of how it would look like at a flood defense system. Where should the BioGrout be placed? Injected? Well, the porosity, permeability is not decreasing that much, but it does decrease, of course, because we add calcite to the soil. And therefore we want to prevent that a new seepage path will occur and it will go through the clay toe. And therefore the levee toe thickness, if it's from clay, it will be about 0.5 to 1 meter thick. So where it's that thick, around that location, we could inject the BioGrout. So it's a little bit, it's at the end of the levee. Istrea has performed the whole erosion test for us to investigate how strong does the BioGrout need to be to prevent the erosion. And we have made columns with 1 flush of calcium urea, 2 flushes, and 3 flushes. And after the whole erosion test, well, they drill in the middle of the core a hole, then they flush water through it, and in the end they'll put paraffin wax in to see what happened, what occurred in the middle of the column. This happened with 2 flushes, and this happened with 3 flushes. 1 flush collapsed immediately, so that wasn't sufficient. And their conclusion was that a double flush of fluid gives sufficient strength for BioGrout. Then we had investigate effectiveness of BioGrout near clay layers. Because, as I said before, it mainly takes the backward erosion, takes place at the interface of a sand-laden and cohesive layer. And we want to know, does this clay have an influence on the attachment of BioGrout? Because if it doesn't attach between a clay layer and a sand layer, you will still maybe get the backward erosion and the piping formation. Here you can see how it should look like in real life, and this would be the experimental setup. We were representing the sand layer underneath the clay core. And we did 2 types of experiments, small-scale experiments and medium-scale experiments. And they actually were the same, only this medium-scale experiment was 4 times larger. And in the experiments we placed 2 centimeter thick BioGrout over the complete length of the experiment, and the depth of the BioGrout varied. Eventually, at the end, we did 7 experiments, 1 without BioGrout to see what would occur if nothing would happen. And then we experiment with different thickness in clay lining and in depth of the BioGrout. Because we were experimenting with the clay lining because the pipe formation is kept in the middle of the experiment. And we want to force that the pipe formation would be along the clay and the sand interface, because that was what our research was for. To show you some, I got 4 short videos to show you the experiments, because we made photos of every 10 seconds. I made a movie out of it. The first movie you will see with no BioGrout. So you can see water flowing from this way to that way, and we put colored water so you could see the water flow. And you can see here the pipe forming, and this is without BioGrout, so eventually you'll get that is, completely. This is what you get if you have no BioGrout. The second one is with BioGrout. but here the pipe is forming in the middle, and here the dashed line is where we place the BioGrout with 2 centimeters, so it's up to here. And as you can see very well, is that the BioGrout is almost as permeable as the rest of the sand. So the color just goes through the BioGrout. And you can see the pipe formation, and it's going to be blocked. You can see some fingers forming, but it's forming perpendicular to the flow up to the clay layers, and then it stops. That is the formation. And the third one, this one, unfortunately we thought that after a critical head, a type of water head, that the water flow would be, the water level would be so high that it would be flowing over the levee. So we stopped a lot of the experiments before failure occurred. And later on, when a colleague of mine did the calculations, she actually wanted to know when did the failure occur and what was the failure. We've got one failure experiment. So this is with thicker clay lining, and you'll get the pipe formation, and then suddenly you get breakthrough through the. So this will occur when BioGrout is not sufficient, and then we have one again where it forms again along the clay lining, but with no breakthrough. And the difference between this one and the previous experiment is here we've got 1 centimeter, so that's 10% of the total depth with BioGrout, but we place the BioGrout in situ. So with the bacteria. And the former one, we scraped off from the 10 centimeters, we scraped 9 centimeters of BioGrout away, forming calcite dust. So the permeability of the soil increased, and therefore we had to make get a really high water head before the piping occurred. So once the water head was really very high, the pressure was so big, it caused breakthrough. These are the analysis of the results for the critical head. So as I mentioned before, we didn't have any breakthrough, so the critical head is this minimum of the critical head, except for 128. And using the Selmayr rule, the critical heads were also calculated. And as you can see here, all the calculated critical heads are lower than the measured critical heads, even for the one without BioGrout. And we don't really know what the reason is, but it could be that it's because of the clay lining. So the width is a little bit smaller, and the width wasn't taken into account into the 2D model, causing maybe this difference. These are also calculated for the effectiveness of BioGrout into the field. We've done this calculations for 2 different failure mechanisms, for fluidization and for breach. And from our experiments, you could see that it was probably breach what caused the failure. But because they saw that some critical heads, when the BioGrout was a little bit, not as thick, was 1 centimeter instead of 10 centimeters, you had a lower critical head, and that is more to fluidization as a failure mechanism. But calculating it for these parameters, so this was the levee that was being calculated for. The fluidization, without BioGrout, the critical head would be 4.5 meters. And with the BioGrout, you get 34 meters. And for breach, you'll get 12.5 meters. But as I said before, unfortunately, we stopped all the experiments before they failed. So we need to do more experiments to really know what would be the real critical head and which of these 2 failure mechanisms would play the largest role. But it's still 3 times higher, minimal, if you apply BioGrout than without BioGrout. As I said, we also were looking for how it would be applied in the field. And if you want to apply it in the field, not only does it work is an important factor, but also how much does it cost if you really want to apply it in the field. For BioGrout, the main costs are the production of bacteria, the treatment of ammonium chloride, and the mobilization and demobilization. So the cost estimation at the moment is between the 500 and 1,000 euros per cubic meter. This depends, of course, on the location, the depth, and the volume. And we have to keep in mind it's a very new technology, so there are still optimization steps to be done. So hopefully lowering the price, but at the moment this is a price indication of BioGrout. This takes me to the conclusions. Well, BioGrout can prevent backward erosion under flood defense systems, but the flood defense system has to have a permeable formation where we inject it. So we cannot prevent erosion in clay and peat layers. And also, we cannot stop the water flow. So if you want to stop the water flow and prevent backward erosion, then also for that BioGrout wouldn't be the method. With BioGrout, the critical head is increased at least 3 times, but as you could see with fluidization, it's almost been 8 or 9 times. But we need further research to determine what's exactly the effectiveness of BioGrout. And taking all these things into mind, we think that BioGrout has a very high potential, especially for multi-flood defense systems. So not for backward erosion, for large places to prevent erosion, but if you have a transition zone or let you say like a pipe through your levee if it's in sand, these spots we could treat very well with BioGrout. It's very difficult to reach them with other measures, and with BioGrout it would be very, I think would be a good measure for those. Thank you very much.
Thank you. Questions? We have 3 questions, and that's it. Start, please, Paul.
Paul Royer from IRCA. I noticed that you mentioned that BioGrout was only applicable in saturated soil. Can you confirm that? And why is it not applicable in unsaturated soil?
It is applicable in saturated soils. But we haven't, it is applicable in saturated soils, but we don't have any experience in unsaturated soils. So I don't know if it's not applicable, but we don't have, at the moment, experience with it. So in Holland, almost everything is saturated. So if there would be an interest in applying it in unsaturated soils, we first have to do some experiments in the lab to see what would occur if there's not a flow.
Okay, so it's not a definitive.
No. It's just a point of attention. Like if you get a question, we cannot say immediately like, oh yes, we can do it. We have to do some tests before we can apply it or not.
Okay, the second question. You want to know?
Yeah. What's the durability? Do you know something about the durability?
Yes. That's actually in our report. We have a big chapter about durability. The durability is with groundwater flow running through. There's like 0.1% loss of calcite if you run it for 50 years. So it's very durable, but of course when it's going to be acid, it's calcite. Your acid, it will dissolve your calcite, but I hope your groundwater wouldn't be very acid. And you have to keep in mind that because BioGrout we produce the ammonium chloride, so we prefer to have a slight increase in strength. So you need less calcium and urea to inject. So the durability in the sense of if you've got vibrations or things like that, that could have an impact on it. But depends on how deep it is and how strong it is. But in chemical durability, it's durable. It's like sandstone with calcite.
You had a question or?
Just to ask the question, yeah? Where do these bacteria come from and how were they discovered?
Where did it come from?
Yes.
Whew. They're soil bacteria. Ours come from DSM. No, they're soil bacteria class 1. So they occur in the soil, but we grow them in a pure culture so that the reaction would be faster. But it's a harmless bacteria. Yeah.
You had a question.
Impact of temperature and how do you prevent them from escaping in the fields as this bacteria?
Yeah, temperatures up to 80 degrees, it's no problem.
And below 0?
I think no, it's between 5 and 80 degrees.
Okay.
And well, as you could see, we have injection point and extraction points. So it's no problem actually if the bacteria will go away, because they will eventually just die because there's no food. The main problem is more that we have the extraction to extract the ammonium chloride. But the bacteria, well, we try to push them, to inject them and extract them, so we'll get the shape we want to have it. And the bacteria they'll stay there because we produce also injected fixation fluid, so they'll mainly stay in the place. But if they'll go somewhere else, after 5 days, 6 days, they'll die. Our bacteria can't die, but they'll go away.
Okay, we have to stop here the questions because we have to stick to the time. In the flood probe stand, we have samples of BioGrout, and we have also the box for the experiments. And at the end, you always can ask questions to Maaike.